Oh, and I did have someone ask like, where are the notes and where are the recordings? So everything's in modules in Canvas. So if you are coming and not actually enrolled in the class and you're not on Canvas, let me know. Let me add you to Canvas. I have no problem adding folks to Canvas regardless of whether you're enrolled, but that's where the notes and recordings are going. So let's start by taking a look at some of these problems from homework 5, and then we'll move on to doing some U-sub stuff. So from homework 5, looks like so request to talk about problem 3, I assume, the population growth problem. So what we have here is, let's just kind of dissect the words for a second. So the number of a certain type of bacteria increases continuously at a rate proportional to the number present. Well, that's kind of gross, but the general form that our textbook gives for that is saying that it increases at a rate. So that's the like at a rate part, meaning we've got a derivative, is proportional to, means that it's equal to a constant times. Like that's what the phrase is proportional to tells us to write. And the number present, that one's a little bit awkward, but this is really what we're looking at. And this is the general form for exponential population growth that the textbook gives as well. Now, other things that we know is that there are 150 bacteria. So I'm going to make that Y. There are 150 bacteria at a given time. Well, we kind of have a choice to make here, but I'm going to call the at a given time t equals 0 for convenience. And if I make that t equals 0, then we're told that there are 450 bacteria 5 hours later. So I'm just going to make that a t equals 5. You do not have to use 0 as your starting point. It's just more convenient numbers wise. So then we're asked a whole bunch of questions about this, but this is enough for us to get our general equation going. So anytime we have this sort of growth where our growth is proportional to the number of something that there is, this is what leads us to a y equals CE to the KT condition. And we can actually get there using antiderivatives, but the book also just gives us that these formulas are connected. Well, if that's the case, then C is our initial condition, which means we can go ahead and write this as y equals 150 e to the KT, and then use this second sort of data point to come up with a value for K. So that second data point, if we plug that in, I've got 450 is equal to 150 e to the K times 5. My objective right now is to solve for K so that we have the full model to work with to answer all of the other questions. If I divide both sides by 150, 450 divided by 150 should give me 3. And then I'm going to choose to write that numerator as saying 5K. I can take the natural log of both sides to get that 5K down and have natural log of 3 is equal to 5K. So our value for K is equal to natural log of 3 divided by 5. If I put all of that back into our kind of generic form for the equation here, we're going to have y equals 150 times e to the ln of 3 divided by 5 times t. So this is our equation for the population growth. And then we're asked a bunch of questions about it. So how many bacteria will there be after 10 hours? That's saying if we plug in 10 for t, what do we get for y? If you were using a calculator, then plug in the 10. If we're not using a calculator, still plug in the 10, just don't worry about simplifying it. How long will it take for the population to double? Well, that how long is asking what's the t value. And if the population is going to double, we started out at 150. So doubling would mean that we were at 300. And then for number 3, does the answer here depend on the starting time? And that's a really interesting question. But the answer is no. So when we're talking about exponential growth or exponential decay, what makes it exponential is that the time it takes to double or the time it takes to triple is consistent throughout the life of that object, or in this case, throughout time for that particular population. Now there's a question in the chat about the difference between CE to the KT and PERT. There is no difference. They are different letters. We tend to use PE to the RT when we're talking about money and finances and continual interest rate. But it functions exactly the same as when we're talking about exponential growth. And it functions exactly the same as if we're talking about radioactive decay. It's really just the setting and the context that change and the actual letters in the equation. But how we work through the equation is the same, regardless of the context. Hopefully that was maybe enough. Question?
Why did you put 150 and not 4?
Here? Oh, yeah. So the C value here is like our initial value. You could put 450. So if you put 450, then this time would be -5, right? So if we're saying that our like frozen moment in time right now is when we're at 450 bacteria, then we were at 150 at a time of -5. So rather than like working backwards in time, I chose to set our starting point at 150. All of the answers to these questions will work out the same either way, but your K value will look different because of your starting point. Good times? So let's take a look at problem 4, which is a PERT problem because we're talking about interest. So problem 4, we have, let me slide this up just a little bit. So problem 4, we have deposited $1,000. And after 8 years, the balance has doubled. So typically when we're talking about money, you actually could use the same letters, y equals CE to the KT, but for compound interest, we usually write this as the amount in the account is the principal times e to the RT. That principal is your initial deposit. So in this case, this would look like A is equal to 1,000 times e to the RT. And then the information that we were given is that after 8 years, so when t is equal to 8, the balance has doubled. So that means that the amount in my account would be $2,000. And that should be enough information for us to come up with an R value. So if we plug stuff in, then I would have 2,000 is equal to 1,000 e to the RT, sorry, e to the R times 8, because we're at $2,000 after 8 years. If I divide both sides by 1,000, I'll have 1/2 is equal to e to the 8R. I'll use my natural log trick again. So natural log of 1/2 is equal to 8R, which means that R would be 8, sorry, would be, that's why I have erasable pens. Good times. R would be ln of 1/2, whole thing divided by 8. Oh, 2,000 divided by 1,000. I did that in my head. Oh, I don't know. Yeah. How about it's 2? Y'all should speak up if I'm making dumb mistakes like that. No, that's not true. It's not a dumb mistake. It was a careless mistake. Someone told me that's what I should call them. I'm just trying to flex. Flexing with my pens. Okay. 2 sounds good. 2. How about that? ln of 2 divided by 8. Whatever that is. Shall we go move into some antiderivative practice? Talk U-substitution a little bit. Okay. See people still writing, so I'll leave that just for a second. I think I mentioned this the other day, but in terms of antiderivatives, if this is your first time seeing antiderivatives, just know that in 16B, we are going to spend like 6 weeks talking about antiderivatives. You are not expected to know how to find every antiderivative right now, but it's really going to be helpful if we're quick with what I'm sort of calling our basics, meaning that if I write something like, and I'll move it on, is it showing up yet? Okay. If I write something like 3x squared minus 10x to the 4th plus 2x, this, we want to get to a space where you're not really writing work for this. You are just writing down an answer fairly quickly. This is going back to our power rule for antiderivatives. So just like when we take derivatives, we multiply by the coefficient and subtract 1. When we do that in reverse, we add 1 to the power and divide by the new power. So when I look at this, I've got 3x squared. So I'm going to add 1 to the exponent and divide by the new exponent. 10x to the 4th, I'm going to add 1 to the exponent, divide by the new exponent. 2x, that's an invisible exponent of 1, but I'm going to add 1 to the exponent, divide by the new exponent. And then when we're done, we add in a plus c because we like to get all of our points on the problem. If you do not like getting all of your points on the problem, it's totally fine to leave it off. I just wouldn't give away those points. Make them work to take points away from you. By the way, each of those fractions could be reduced. So if you prefer to just do those numbers in your head, we could have gone straight to x cubed minus 2x to the 5th plus x squared plus c and called that our general antiderivative. I don't remember exactly which problem we left off with. on Monday, but I like wrote a problem that kind of came from a chain rule. We don't need to do exactly that problem today. I'm just going to make up a new one. But yeah. Like what would be wrong if you left it off? So you would not have taken into account all possible functions whose derivatives are equal to 3x squared minus 10x to the fourth plus 2x, right? So this question is asking like what, when I write this notation wise, it's called an indefinite integral because, well, part of the indefinite part is that there are an infinite number of functions whose derivative is equal to this, but they all differ by a constant. So we have to include that generic constant in there until we have more information about the problem, right? So if I were to tell you, I could write this in a different way, right? If I said something like dy dx is equal to 4x to the 7th plus 3 and y of 0 is equal to 8. I have now actually given us enough information to figure out what the true function was. So my first step here, if I was trying to solve for y, well, this part is telling me that we have this thing that's the derivative. So to take the antiderivative, part of our notation for that is to write this definite integral thing. Kind of looks like a big S of 4x to the 7th plus 3. Well, when I find that antiderivative, right, I'm going to add one to the exponent. So I'd have 4x to the 8th divide by the new exponent. Whenever we have a constant, that constant came from taking the derivative of the constant times x. The derivative of 3x is equal to 3. And then I could add in a constant. Well, here I have this extra piece of information, and that extra piece of information could let me get rid of the c. Because now this is sort of like my generic or my general equation for y. But now I know that I should get 8 when I plug in 0 for x, which means that the value of that constant had to be 8. So my actual specific function that meets both of these rules would be that y is equal to 4x to the 8th over 8 plus 3x plus 8. But unless the question is asked in such a way that we kind of have this extra information, we've got to just leave it as a plus c after we find the antiderivative. Dun, dun, dun. Good times. So now let's talk U-substitution for a minute. If you have seen U-substitution in a previous life, that's okay. Just pretend you haven't for a minute. Hang out with me. Pretend you haven't seen U-substitution before. Maybe don't even take notes for a second. And we'll just kind of get a first problem going here. So even if you can already see what the answer is, hold off and pretend you can't. Let's see. I'm going to have x cubed plus 2x to the fourth, and x squared plus 2 dx. Okay. Because we're going to have a whole bunch of different techniques for finding antiderivatives, like one framework and kind of a starting point that I like to use is to look at something and say, well, is it algebra, is it trig, or is it a mixture of stuff? And I'm calling this thing just algebra because we only have numbers times x's raised to powers. So I'm putting that in the broad category of algebra. And if it's algebra, the next question I'm going to ask myself, does the derivative of one part equal the other part? And what I mean here is there's kind of two pieces, but one part of this is the derivative of the other part. Has anyone studied a second language or a third language? Is there a language that anyone has always really wanted to learn, but you haven't had a chance to yet? Ooh, like everyone's got a language. Okay, I got to hear them all. What's your language? Japanese?
Spanish.
Did you have a language? You don't have to have a language. No? Okay, cool. I've always really wanted to learn Portuguese, but I haven't made the time to do it, right? So we got Italian as the vote on Zoom. So none of us said, let's see, Navajo. Does anyone speak Navajo? Okay, maybe it's a bad example because I think they don't have a written language. Okay, also nobody said Danish. Does anyone speak Danish? Okay, Danish it is. So pretend we're all taking a Danish class together and someone just, it's like our first day of class and the teacher asked us a question in Danish. Well, the first thing I'm going to do is go find the dictionary and translate all of the words into a language that I do know fluently. So I'm going to do the same thing to this math problem. I'm going to take this and I'm going to build my dictionary. And the way I'm going to build my dictionary is I'm going to find the part whose derivative is in the problem, and I'm going to call it U. And over here off to the side, I'm just building my dictionary. So I'm going to have U is equal to x cubed plus 2x. Now my objective is to translate everything in this problem using something from my dictionary. So right now I would be able to translate this part. This could be translated as u to the fourth. But this other part needs a translation also. So I'm going to come over here and I'm going to take the derivative and get 3x squared plus 2, which almost looks like stuff over here if I just rearrange it slightly. Because if I multiply both sides of this one by dx, then I have du is equal to 3x squared plus 2 dx. So now I have something in my dictionary that I can translate this part with. Now, just like if I was asked that question in Danish, I've now translated into a language I can deal with. I'm going to find the answer. So add 1 to the exponent, divide by the new exponent, plus c. But then I'm taking a Danish class, so I probably have to go back and use that dictionary again to write my answer back into Danish. So I'm going to look to my dictionary over here and say u is equal to x cubed plus 2x. So I'm going to translate this back to x cubed plus 2x to the fifth divided by 5 plus c. That's my final answer. And that's really the whole deal with U-substitution. We're going to build our vocabulary list, translate the problem, answer it, and then go back. If anybody wants that in your notes, I'll give you a chance to get caught up with that problem in your notes. And then we'll do some more examples. Should we cruise to another example? Now, it doesn't always work out quite as nicely that like everything we wanted is perfectly there for us. So maybe we've got something like the square root of x to the fourth plus 2 times x cubed dx. I'm going to walk up to this question and I'm going to say, was the algebra trigger a mixture of stuff? It's just algebra. So is the derivative of one part equal to another part? And the answer to that question is, well, yeah, kind of. Who's the part whose derivative is almost in here? Totally, like the x to the fourth plus 2 part has a derivative that's almost x cubed. So I'm going to come over here and build my vocabulary list. And if I let u be x to the fourth plus 2, then that derivative would be 4x cubed. Now I'm writing this out as a derivative, but functionally, what I usually write instead of this step is I skip ahead to writing it as the differential, meaning that I've already multiplied both sides by dx. So I would actually write du is equal to 4x cubed dx. And that's what I would put in my list. So now I start looking over here at the problem. This part would become the square root of u. But I don't exactly have that x cubed dx. Isn't exactly what I have in my vocabulary list. But if I divide both sides by 4, it will be. So 1/4 du is equal to x cubed dx. And that's what I'm going to translate this part into. Question?
So let's say that both of them are like completely like not even close to be like derivatives of each other. Will we just resort back to the regular antiderivative, or would that be another method?
We'll probably have another method. Yeah. So for now, from what it looks like on the practice test, the problems you will either be able to handle by turning them into like it's directly an antiderivative, or they're going to use this substitution method. Yeah. We will build more methods, but in terms of this exam, I think this is it. Just those two options. Well, I have options for how to get through this, but I probably want to rewrite that square root of u as u to the 1/2 power. So I'm just going to take this and write that as the integral of 1/4 u to the 1/2 power, so that we can add 1 to the exponent and divide by the new exponent. So I would have 1/4 u to the 3/2 and then divided by 3/2. Since I've got a fraction divided by another fraction, I can switch that to be multiplying by the reciprocal. Okay, and I can write that as 1/4 times 2/3 u to the 3/2 plus c, and then make my fractions a little nicer. Don't have to do that step, but it's kind of nice. So my fractions will turn into 1/6. And to make sure that I get all my points, I do want to go back and use my vocabulary list again to translate that u back into x to the 4th plus 2. So if your question was asked in terms of x, we just want to make sure that in the end, we've answered it in terms of x. Questions about this one before I, yeah.
Does U-substitution only work when there's squares, like the 2 halves? Or can it always?
That's a really good, so U-substitution works whenever one piece of it is equal to the derivative of the other piece. But let's do a slightly messy one, just because we can. Because sometimes it's less obvious to see that one part of it is the derivative of the other part. Oh, sure. How about if I had, I don't know how messy to make this. Not crazy messy, right? Just slightly messy. Let me go with e to the x plus 1 over e to the x plus x. Yes. Well, the good news is we don't actually know how to do anything else. So if you can't just see what the antiderivative is, it's probably a U-substitution. So if I walk up to this problem and say, oh, is it algebra, trig, or a mixture of stuff? This is actually one of the problems that I would call a mixture because it has exponentials in it. Since it's a mixture problem, that first question I'm really asking myself is, does the derivative of one part equal the other part? Does it? So to be good with antiderivatives, it's important that we're good with derivatives. So to me, when I look at that and I'm saying one part or the other part, I'm really thinking about the top and the bottom. So if I look at the top, what's the derivative of e to the x plus 1? Totally, it's just e to the x. What's the derivative of e to the x plus x? Yeah. So the useful vocabulary swap here is to call u e to the x plus x, so that my du, or the derivative of that, is e to the x plus 1 dx. Well, this one's a little bit messier to look at when I do my vocabulary swap, but the denominator down here is U. And that whole numerator part is du. Or if you prefer to look at it as 1 over U du, you can as well. This is that special one related to the derivatives we've been taking. What's the function whose derivative is 1 over U? Chapter 4 is kind of all about exponentials and totally, this is natural log in disguise. The derivative of natural log is 1 over x, or really just 1 over something times the derivative of the something. So this is going to become natural log absolute value of u. And that absolute value, again, is to make sure that we're preserving that the domain of 1 over u, as we can plug in positive or negative values. So we want to make sure that we can still do that after we take the antiderivative. But now I'm going to swoop in. The question was asked in terms of x's, so I've got to take it back to x's. And then because we're prepping for an exam, could we simplify that final answer using log rules? I'm going to take the silence to be the correct answer of no, we cannot simplify that using log rules. We do not have a rule if we've got addition inside of a log. If that were multiplication, then we could break it apart. But for addition, that's it. Addition inside of a log, we're just going to leave it alone and walk away. Correct. Yeah, addition or subtraction, either way, if it's inside of the log, we're walking away. Should we practice some more antiderivatives? Okay. I think I've got space to squeeze one more in here. And let's go for antiderivative. So I'm walking up to this question. I'm thinking, is it algebra, trig, or a mixture of stuff? And it's just algebra because I just have x's raised to powers. Is the derivative of one part equal to the other part? I'm going with no, because the derivative of x squared plus 1 would just be 2x. I could deal with the constant, but the subtracting 3 is the problem. This one is not a U-substitution. This one, we really should just multiply the stuff out and make the whole thing look like x is raised to powers. So if I start distributing out x squared times x will be x cubed, and then minus 3x squared plus x and minus 3. And then we'll just apply our power rule to each piece. So if I integrate x cubed, I'll add 1 to the exponent, divide by the new exponent, add 1 to the exponent here, divide by the new exponent, add 1 to the exponent, divide by the new exponent, add 1 to, well, I get negative 3x plus a constant. as a general rule, if I've got a polynomial times a polynomial, you can do that quick check for a U-sub, but you're probably gonna have to multiply that out. And the other thing that I wasn't sure about, did you all talk about finding derivatives if the base is, oh yeah, you totally did. It's on homework 5. Let's say we didn't really talk about finding derivatives if the base isn't E, or it's like a regular log and not a natural log. So I thought maybe we could take a minute and talk about those. So well, let's say that I had y equals 5 to the x. There is a formula for this, for finding the derivative. We can totally just use the formula, but I'm going to show it the long way first, and then we can skip to the formula shortcut. The long way is to put back on our 16A hats and to use some implicit differentiation. So if I look at this and I take the natural log of both sides, then over here, when I take the natural log, I'm going to end up with x times natural log of 5. And then I can use implicit differentiation so that when I take the derivative of natural log of y, I get 1 over y times y prime. And when I take the derivative on the right-hand side, even though it feels like it's not, natural log of 5 is a constant. It's just a number. If you put it in your calculator, it spits out a number. So a number times x, when I take the derivative, will just be that number. By the magic of algebra, I'm going to multiply both sides by y because I'm trying to get the y prime by itself. So I've now got y prime is equal to natural log of 5 times y, or since y in the original problem was 5 to the x, y prime is equal to natural log of 5 times 5 to the x. And if I were to like repeat this process for any number as a base, if I have y is equal to a to the x, where a is a number, we would do all of this and end up with y prime is equal to natural log of a times a to the x. Now, based on where we get in the end, there is something that has to be true about a. A is not just any old number. It's going to have to be, yeah. Good times. Now, we can also do things like apply the chain rule to this. So if I had y is equal to 3 raised to the x squared, then I can take the natural log of both sides, right, and work through with the implicit differentiation. Or we can use this new rule to say when I take the derivative, I'm going to get natural log of the base times, put that whole exponential piece back, and then just remember that the chain rule means we need to multiply by 2x.
And we can leave it like that.
Yeah, for sure you can leave it like that. So we have this rule for when we're doing derivatives of exponentials with different bases, and we can also talk about what the rule is when we have logs of different bases. So if I had y is equal to log base 2 of x, and honestly, I think the easiest option when we're talking about logs,
Just to change it to exponential.
oh, yeah, so there are two, like, that's an option, is to change it to exponential form and then mess with it. I was actually gonna say that I prefer to just use this fact from pre-calculus. It's called the change of base formula. And you can choose any, you can change any log base into a natural log base. So it comes from the change of base formula. And then I think it's pretty straightforward then. Well, when I take the derivative of this is like saying 1 over ln of 2 times natural log of x. And 1 over ln of 2 is a constant, so it's just going to stay there with us. And then the derivative of ln of x is 1 over x. So more generally, if we have log with any base b of x, then the derivative is going to be 1 over natural log of the base times 1 over x. And both of those generic formulas, the one for a to the x and log base b of x, those are both in our textbook.